Hello, students. So I'm Professor Sarish Dasgupta. I teach at Dhirubhai Ambani Institute of Information and Communication Technology. That's in Gandhinagar in Gujarat. And I've been teaching, among other things, but I've been teaching neural NLP and NLP over there as well. So hopefully I will see a enthusiastic crowd. So today's lecture is about advanced attention mechanisms. So by advanced, what we would want to focus on is different optimization techniques, right, in terms of time and space complexity. And we would see what are the new research that has happened so far. We'll cover some of the most important ones and we'll try to understand them. Okay. One thing I want to tell you is that no rocket science involved. It's pretty common sense. Once you get through this material, you'll see that it's pretty common sense. So it's not something that's difficult to understand. Okay, so let's just have a very quick recap of what self-attention is. So basically, in a full complete self-attention, what you would do is you would have this query matrix, right? So the query matrix would be basically a sequence would capture a sequence of tokens. Let's say if I have John loves ice cream made in India, then John would be one of the row vectors, loves will be one of the row vectors, and so on of Q, right? And the idea is to get the contextual embedding of Q, right? So what we usually do is that we have two different vectors. One is the key vector and one is the value vector for each single token. So the objective being that the token we have to get the contextual embedding of the token, right? So we first convert the token into a query vector, and we call it query because that's basically the target. That's what you are trying to get at. And then we look at the value, right? So which means to what extent the context tokens influence that particular token. So if I say John loves ice cream made in New York, so to what extent John is influencing love? If love is the query, to what extent ice cream is influencing love, and made is influencing love, in is influencing love, and New York is influencing love, right? So the idea over here is that we try to take certain percentage of the influence as is, and we say that, okay, to what extent? When I say to what extent, what it means is that what is the percentage, right? So if I have to say, let's say John loves ice cream made in New York, and let's say if this is my query, then what I'm trying to do is I'm trying to see what is the percentage of influence that each one of them have individually, independently. So what is the independent influence of each one of them on loves, right? Now, when we do that, we consider John to be the V, okay? Ice cream also is another V, made is a V, in is a V, and New York is a V, right? So these are the values. So V stands for values, right? So that constitutes the value matrix. And of course, love itself. So this is something interesting, that love itself can influence it, itself, right? But then this percentage is computed in terms of the dot product, which is a similarity between loves and John, but as a key. So you have two different avatars, so to say, of John. One is John, which influences, and one is John's key, which is sort of a representative of John, which tries to figure, so that you can understand to what extent Loves is similar or related to John. And the idea behind why John K is important and why it should be different than John V is because while John can be something that is quite unrelated or not that similar, but is influencing in a language modeling sense, in terms of love. But then if that happens, then John's embedding would be quite far away than Love's, and then you wouldn't get a good dot product. So the idea over here is that you don't necessarily have to be close in a neighborhood in order to influence somebody. But how do we then do that? So that's why you need a representative key of John that would now go and do the dot product with Love. So that's the essence. That's basically the essence, that while if I have to influence you, I don't really have to stand beside you and then influence you. So my representative is going to go beside you, and then we will figure out to what extent you are similar to my representative, right? So that's the philosophy. And that's this key. And then you do this similarity computation. So dot product would become, if you want to look at it as a multiplication, it becomes you take the transpose. And I am not going to do the softmax. So when you do the softmax of this, in the example you don't have the softmax, but when you do the softmax of this, you get the percentage, right? So that's how you get the percentage. So that's the thing. To what extent of John's vector or embedding will I bring it inside Love's embedding and add it up or combine together to form the resultant Love embedding, right? And that becomes a contextual embedding, and that's contextual embedding is also called attention. So you can also look at it like this. So this is a contextual embedding of everybody. So this is a matrix, so it will have the contextual embedding of John, Loves, ice cream, everyone, right? So that's what it is. And so this is a recap. Now when you look at a causal attention, which means if you're looking only at the decoder of the transformer, or a decoder only transformer based model like GPT style models, you'll see that you have something called forward mask. I guess you have already studied this probably, but just again a very quick recap. So in some loose sense it is called causal. Why? Because this attention, you are restricting the attention in a way such that Love is not allowed to be influenced or to get the influence from ice cream made in New York. Love can only get the influence from John. And similarly, ice cream cannot get influenced by made in and New York. Ice cream can only get the influence from John and Loves, and of course ice cream itself. So that would mean that you need to mask whatever is in front of a particular token, right? Or whatever is upcoming. And the way to do that is you just put a minus infinity in front of, let's say, if the sequence or the sentence is the cat is on a chair, then after you just keep everything as minus infinity. You don't show it. So minus infinity, when you plug it into softmax, it becomes 0. So we have not shown the softmax over here, but when you plug that into a softmax, it becomes 0, right? So and this is how causal attention would work. And from here onwards, we are going to focus mostly on causal language models or causal attention. And we want to understand that whether we can optimize the causal attention in terms of time and space. So if you carefully look at what's happening in terms of the time complexity, you see that over here you first have a dot product that's going on between q and k, k being the representative, right? So that dot product is represented by this. So this is the dot product, this is the similarity, right? And this takes n square multiplied by d, where d is what? The dimension. So what is the dimension of each token, right? So n square, why n square? Because you're just doing q cross k, k transpose, and that would give you an n square time complexity. After that, you do a softmax, and the softmax would take n square, and then you again do the multiplication with v, right? So that's the final multiplication. So the percentage being multiplied with the v embedding, and you are adding up all the v embeddings, so that would take another n square multiplied by d. So that overall the complexity becomes big O of n square multiplied by d. And the space complexity, on the other hand, you start with q and k and v. So that's this. So 3 times. So you have q, you have k, and you have v. So you have 3 times n multiplied by d, where n is the sequence length. So by the way, n is the sequence length. So in this example, what would be the sequence length? 1, 2, 3, 4, 5, 6. So 6 is the sequence length. So 6 is the sequence length, right? So n is the sequence length. So 3 times n multiplied by d. So that's to store q and k and v, and then you have n squared. So that's again the storage that is required once you do the dot product, and then you have n multiplied by d, which is the final storage that is required for the attention matrix or the scores, right? So how much you would so the final attention or the contextual embedding, so the storage that is required to store the contextual embedding, so that is n multiplied by d. So overall, that would mean that you have n square plus n multiplied by d complexity. So if you want to look at it from in terms of what is the byte size, then that would be like 3 times n multiplied by d plus n square multiplied by the size of a float. So if the float, if you're taking, let's say 16 bit, then it would be multiplied by that many number of bytes. If you take 32, then it will be multiplied by that many number of bytes, and so on, right? So whatever is your architecture, or whatever 64-bit, if you take 64-bit, so whatever is the precision, so that many number of bytes. So that would be the exact space complexity, right? And how it is computed, you can look at the animation. So as one query comes after the other query, so you have the query coming in, so token 1, then token 2, then token 3, then token 4, and at the same time the keys are also being stored. They are also coming in, and then the QKT, which is the dot product, so that is being computed, keeping the forward mask in place, right? So every time you are for every row, you're computing everything all over again. So that's what is going on over here, right? So so can we do better? So that's the thing. So why do we need to do better? So first of all, again, the context is what? Causal. Causal means you don't look at what is upcoming, right? You look at what has already happened. So if you look at it from that point of view, you'll see that, so when you look at this particular row, which is the second query, when the second token comes in the query, right? So you will see that this part is already computed before, isn't it? Right. So you're just kind of like almost recomputing the same thing which you have already computed. When you look at the third row, you'll see that these two things are already computed in previously, right? And recursively, this one has already been computed previously, right? So essentially, what you're doing is that you are unnecessarily computing the same thing over and over and over again as new keys, new tokens come in terms of the query, right? Uh, Interestingly, if you look very carefully, you'll see that since it's a language model, you're always interested in what's going to happen now or next, right? You're not really interested in what has already happened before, right? Because the entire point of language model is to predict the next linguistic unit. So in our case, if the linguistic unit is a token, so the problem becomes what is the probability of the next token, right? So essentially what we are really interested in is this. So this is actually the goal. Yeah. So this is actually the goal, right? So this is what we are interested in. Although we have to keep computing whatever is happening before, but this is actually the goal, right? And interestingly, while calculating this goal, this part is already computed before and we are still recomputing it. So that's the problem, right? So this is getting recomputed unnecessarily. The first three parts, right? Okay, so what is going on is we also don't need to, another thing that you need to understand is we also don't need to store, no need to store this, the first four things, and it's only this one that we are interested in. It's only this final one. That's the goal. That's what we are interested in as a language model, because that's the token that we want to predict at every time step, at a particular time step, right? So that's what we is mostly interesting. So what we would see is something called KV caching or key value caching. So the idea is very simple. I mean, it's just that, why do you have to recompute something that you have already computed? So what's the idea? The idea is cache it. As simple as that. Why don't we just cache it and then just read it from the cache? Simple idea, right? So this is basically the difference. The animation shows you a very clear difference of what is the difference between something without the cache and something with KV cache. So this is with KV cache. Okay, so in KV cache, what happens is that you don't pile up your queries as well. As you can see, first, that's the first difference, which is in the query. So the query, you are not trying to pile up the query. Why? Because you don't care about what has happened in the past. You care about what's going to happen right now. What is the next thing to happen? That's what you care about. So you don't pile up token 1, token 2, token 3, and token 4. You just take one at a time, right? So that's the first thing. So instead of 4 cross D, you're only always going to deal with 1 cross D, and as far as the query is concerned. So it's basically always 1 cross D instead of N cross D. So that's the first thing. The second thing is that you're in the same way, of course, the key is also going to work in the same way, but then you cannot really forget K1 and K2. Why? Because you can't forget K1 and K2 because at the end of the day, when I'm dealing with IC, let's say, when I want to understand what is the influence of IC, I have to look back at Love's and I also have to look back at John. I cannot simply forget John. It cannot be like, oh, I'm only dealing with love. No, I have to look back at John. But John's influence, I can do something because I know the K of John. I don't have to recompute the K of John. So I can just cache it and get that K of John from here, right? So the key, so when I look at token 2, then token 3, then token 4, so what is happening over here is that the purple ones are actually being fetched from the cache. So instead of being recomputed, is being fetched from the cache. So essentially, your KT, as it grows, it starts fetching the previous Ks from the cache, right? So that instead of recomputing it all over again. And then finally, the most important part, which actually gives us the optimization, is over here. So what is going on is that you don't maintain a matrix like what was happening over here, right? So you don't have to maintain that matrix because all you care about is a specific row at a specific time point, right? So that's all you care about. Why? Because all you care about is predicting the next token, and that you can get only from that particular. You don't have to need to know about the entire matrix. You can get what to predict from that particular time step row only, right? So basically, I don't care about the first row or the second row or the third row or the fourth row, or sorry, the third row in this example. As I progress, I just keep going on and compute this thing. So when I talk about query token 4, I only look at what's the influence of K1 on query token 4, K2 on query token 4, K3 on query token 4, and K4 on query token 4. And that's the last row. That's the last row. So I don't care about the third row and the second row and the first row, right? And again, when I look at the value, I need the previous value, but I would just fetch it from the cache. Why I need the previous value? Because again, in order to get the final contextual embedding or the attention, I need the previous V's also, because I have to finally get the arrows, the incoming arrows from all the V's which were in the previously previous to a particular token. So essentially, so again, I am getting all this from the cache, and what matters is this final value or the final token, and then I am only interested in token 4. So that's what I'm only interested in at time point T4. So if at time point T5, similarly, you can generalize. I'm only interested in token 5, and so on and so forth. So that's what I'm doing. So with KV caching, what is going on is that I can actually drastically reduce the complexity to n multiplied by t, the big O. And from a byte point of view, while previously I was having 3 multiplied by n multiplied by d plus n square whole multiplied by the size of the float, right now I can just do it with 2 multiplied by n multiplied by d. That's it. I don't need an n square because I don't have to create that matrix, the square matrix. I don't need the square matrix. So the n square goes away, and I'm only dealing with 2 because I'm not piling up the query. So one of the 3's are gone. So I'm only dealing with 2, which is k and b, right? So that's the idea. So that's one way, and this is the KV caching. If you look at any kind of modern implementation of language models, you will see that everybody does KV caching. So it's not that it comes with KV caching. So KV caching is basically a part of it. By the way, one caveat, one important disclaimer. Right now, we are only talking about one head and one layer. Now, the same thing, the same animation is happening in every head and every layer. So, of course, if you look at the complexity, you might ask me that, sir, well, where is the number of heads, so you should multiply it with the number of heads. And where is the layers, so you should multiply with the number of layers. And I said that yes, that's correct, but this complexity computation is only for one head and one layer, so you can just multiply it with the number of heads and the number of layers, right? So that is something that we have to understand. Okay, now that was like year what, 2017, right, when transformers came in, and then people came up with KV caching. Now in 2020, like somewhat around 3 years later, Allen Institute for AI, they came up with this interesting idea, and they said that for many NLP problems, you really don't have to get the influence or the incoming edges from everybody. You don't have to do that. Which means your context window doesn't necessarily have to be very long, right? So right now, John loves ice cream made in New York is a very small sentence. But let's say you have like multiple sentences and you are trying to, like a whole paragraph or maybe a whole page of a document, and you want to get the influence from all over the place, sort of, to a particular target, so incoming edges coming from everywhere. And what these guys said, or rather showed, is that for many NLP problems, you don't need that much of context window. You can just fix a small context window. Let's say the window size maybe fix a window size, maybe small w, and w can be maybe 4, 5, whatever, 6, whatever you want to keep. So this is your contextual context window, rather, and it can suffice for most of your problems. So which means you don't really need the full and square attention. So if you have John loves ice cream over here, let's say John loves ice cream made in India or New York, whatever. And if you have John loves ice cream made in India, I'm pretty shabby in terms of diagrams. So you don't really need to compute everybody with everybody. So what you can do is you can take a window size. So like over here, the window size is how much? W is equals to 1, 2, 3, 4, 5, 6, 7. And what you do is you take the first one. The first one do not have anything in before it, so you just go after it, and then you take the first 1, 2, 3, 4, let's say, and then you take the next one, and you then take the 4. So basically 7 would mean that plus 4 over here, and plus 3 and minus 3 in terms of particular target word, right? So if this is the word, so plus 3. If this is the word, then plus 3. And once this is plus 3, and this is minus 3. So you just like how you design a context window. So you have plus 3 on this side, minus 3 on this side. But this, of course, doesn't necessarily have to be applied on, whatever you're seeing right now doesn't necessarily apply on causal language model, which means that you are able to, in this particular diagram, you are able to get information from the future in order to build your attention or contextual embedding, right? So in this diagram, you are not really causal. So this diagram is for any LLM, not just causal. But can you do it for causal? The answer is yes. You don't have plus. So if you have to do it for causal, then this does not apply. This does not apply for causal LM. So you only do the minus. You don't do the plus. So that's the only difference, right? So self-sliding window, and this is called sliding window because you are sliding the contextual window at every given time point. So the idea is, again, simple. You don't need all these white spaces is because you don't need them. That's the hypothesis. That's a linguistic hypothesis that for many NLP problems, you don't need that much of gathering of information, right? You don't need that much of influence. Okay, so an example in our case would be this sort of a thing where in continuing with the previous example, so your minus infinity will all become 0, and this is causal, by the way. This is an example of cause sliding window applied on causal. So where your everything coming up is all 0, and you have a W size of how much? 3. So the first you can't apply minus 3. The second you can't apply minus 3. From the third you can actually apply minus 3. Right, so that's how it works. Okay. What happens to the KV cache? Let's say that we are also applying KV cache to sliding window. Nobody can stop you from doing that. You can always apply, because the KV cache issue, the problem that we discussed in KV cache, that you're recomputing over and over the same thing, also applies over here as well. It's just that you're not seeing everybody, but you're seeing some people, and the same recomputation will happen even here. So you can get rid of that recomputation even in this case, right? The only difference being, instead of everyone, you're just saying the W. That's the only difference. Otherwise, everything remains the same, right? So, again, when a particular token comes, let's say this is token number 8 in this particular example. This is token number 8. So when token number 8 comes, you need to cache till 7, and it should come from this cache. So you're fetching till 7, you're fetching the keys from cache, and since it's sliding window, you don't need all of them, so you only need this much, right, which is in purple. So 4. So if your W equals to 4, so you don't need all the 7. So instead of 7, you go for 4. So basically 1, 2, 3, 4. So this is how much you fetch. You don't fetch everybody. So the idea is, do not fetch everyone. But just the 4, whatever, just the W. And again, when you are finally trying to predict what's coming next, you don't have to have an entire prediction matrix. You just predict only what's coming next, which is the output token of 8, which is the contextual embedding of 8. And for that, this is the W. You just need the W. You don't need the N. You don't need N. You need W. You don't need the entire sequence. You need W. So that's the thing. So what's going on? It's very simple. What happens in KV caching, or the KV cache storage? What happens is that instead of N, it gets replaced by W. Everything remains the same, right? So bit more compression of the storage of the KV cache. So basically you end up spending less GPU memory if you do this, right? What about the space complexity? Again, it's a bit low because it's no more n, but it's w. So this w comes up and it adds on to the space complexity. What about time complexity? Again, because of the because of the because of the w. Okay, by the way, there is an error. There is an error. So this would be n multiplied by w multiplied by d. This is, instead of this, n multiplied by w and then multiplied by d, right? So, and then you get this complexity. So basically the time complexity also reduces. So essentially it helps you to have better inference and better faster inference and faster training. So that's what happens with sliding attention. However, in many cases, in many tasks, NLP tasks, sliding window attention will not do well. What kind of work? What kind of task? As an example, let's say you're doing a dialogue chaining kind of prediction, where you are essentially initiating a dialogue with a bot like ChatGPT or something, and you need to keep a long history, right? And over there, the sliding window will not work that much because some influence may come from a conversation that happened maybe even yesterday, right? So you need to maintain longer contextual window or context window for many other kind of NLP problems, right? Uh, so that's the, or maybe something is very descriptive, extremely descriptive. Let's say you want to explain something, in a language model that is able to explain what it is predicting. So, and this explanation involves a lot of, let's say, explanations related to, let's say, physics or other kind of mathematical reasoning and so on, right? And that takes up a good length. So it's not, then you can't really limit the context window only to a few tokens before and ahead or before, and expect that it will give you good results. So it can end up giving you, so even though you speed up the process and everything for several other kind of NLP problems, it won't work, right? Okay. So now let's go back to 2017. The attention is all you need paper got published in Europe, right? So what happened at that time was they also realized something else. So apart from which you have already studied, so apart from dealing with only one head, they felt that, okay, why not do the same thing or repeat the same thing independently by using multiple heads, right? So why not do the q dot k and then get that percentage, apply that on b, add it up to get the contextual embedding? Why not do that separately everywhere in many different places in a particular layer, right? The rationale, what was the rationale? What was the thinking behind it? The thinking was that while when you do that, you may be able to capture certain relations, certain incoming edges that you are not able to do in one particular, using only one particular single head. As an example, let's say that you have John and you have ice cream, and there is an edge from John coming into ice cream, right? Now, what does that edge signify? Does that signify that John has a lexical relationship with ice cream, which means when John You get to see John and ice cream a lot of times. They co-occur a lot of times. Does that what it signifies, or does that signify that you have a proper noun, John, and you have ice cream, which is a common noun, and they are associated closely? It can be both, right? So you can look at it at a lexical association level, you can look at it at a syntactic association level, right? So, and then the syntactic association, there are so many types of syntactic associations. And there are so many types of lexical associations also, right? So, but when I say lexical association, it may also mean that they go together or they don't go together, whatever that is. So, what if I have to capture all the different aspects of an association, right? Now, that cannot be captured with one edge, having one percentage, because one percentage of the weight or the information coming in, the inward information, will only correspond to one kind of association. Like, what is the strength of this association? That's all you can say. So if that is 50%, let's say, if the percentage is 50%, all that you can say is that, okay, with 50% of association strength, I can find this particular kind of linguistic association. But what about other kind of linguistic associations that may happen between two tokens? So how about that? One of them can be 72, another can be 41%, another can be 53%. So what about that kind of association? So for that, what I do is I repeat the process independently, right? And that's what is multi-head self-attention. But by doing that, what am I doing? I'm creating some trouble in terms of the time complexity and the space complexity, because I am multiplying whatever is my big O, the worst case complexity, I'm multiplying that with the number of heads. Let's say the number of heads being the number of heads, let us assume that is H, right? And what is going on right now is this is H1, H2, H3, H4, H5, H8, let's say in this example. And in each of the H, what is going on? In each of the H, this Q dot K is first happening, the similarity, getting the percentage, applying that to the values, and then adding it all together, right? So that's going on at every single head, right? So that's the thing. Okay, so now 2 years later, a paper came up from Google. That was Google Brain, but this is Google, and they came up with an optimization technique, and they called it multi-query attention, MQA. So what happens in multi-query attention is very simple. So what they said that they didn't like the idea that you are using, every head is using separate keys and values, right? So what they thought is that, why don't we do something? Okay, I can understand that you need to have different associations for ice cream, how ice cream is related to John in all sorts of ways. So that's why you need different heads, because each head has to figure out what are, for each kind of aspects, sort of as if like there are 8 aspects in this example, and I have to figure out how ice cream is related to John in 8 different ways in terms of lexicosyntactic variations, right? So what they said is that, okay, let's try to do this experiment, and let's say that while the queries will differ, the Q's will differ in different heads, but the K's and the V's won't differ. And what is the logic behind this? The logic is that I am looking at, let's say I am a value, right? And you are all queries. And I'm looking at each one of you in different ways in terms of what is our relationship, in the classroom, on the playground, in the gym, and so on and so forth, right? What is our relationship? And I'm looking at that, but I'm looking at you as a different personality in every single context, right? So that's what is going on. So while you are different and in every single location, but I am not different in the sense the way I will process you and take a decision about how much I should influence you, that my personality do not does not change. My personality remains the same irrespective of whether I'm in the classroom or whether I'm in the gym or whether I'm in the playground with you. So to give you an analogy, so that's the philosophy over here. And that's why, since I am single and I'm looking at you, my personality is not changing. Therefore, my representative's personality will also not change, which is K. K is my representative, right? My secretary, sort of. So K is not going to change as well. So there will be only one K, right? So your personality is changing. Always remember that. So as you move from one place to the other, your personality is changing, but my personality is not changing. So the people who are going to influence you, their personality is not changing. While you are changing from one context to the other context to the other context, so that's the idea, basically. And that's why it's very simple to understand why it should be the cache size should be reduced by a factor of h, because that was getting multiplied before, and now it gets dropped off. So the overall reduction of the KV cache size will be by a factor of h, right? So that's multi-query, as simple as that. Now, what's the problem with this approach? The problem that was found later on, and quite later on, in fact, sort of like, I think last year, EMNLP, that's when it got sorted out, sort of. It got released. We came to understand that, there is a decline in the performance quality, of course, because this very assumption that the influencer's personality does not change is also not true. So you made that assumption, right? That the influencers, while the guy who is getting influence gets changed, its personality changes, but whoever is influencing them, their personality don't change. Now that's an assumption, and that's not a correct assumption, right? And that's why, obviously, certain degradation will happen in terms of the accuracy, and that what happened. But then there's something else started happening, which is a training instability started. We started to see certain kind of training instability when we started training these sort of models, right? Now, because of that, sometime around 2023, a paper came up. This paper came up in 2022, was in ArcZip for a long time, and then got accepted in ICLR in 2023, and that was by some people from Georgia Tech and Google Research. And they came up with this idea that, okay, why can't we do something like this? So instead of having one key and randomly initializing that key, and then corresponding V, randomly initializing that V, and well, technically speaking, you don't initialize the K and the V, but you initialize WK and WV. So that's what you initialize. So instead of randomly initializing that, why don't we do something? Why don't we take a proper model that was working well, like a proper MHA model, multi-head attention model, let's say transformer or T5 or whatever, which works well, or even GPT 2, 3, 4, whatever, works well. Take all their keys after the training is over. Take their keys, or take a snapshot, a particular snapshot that is working well. Take the keys, and then what you do is you make a mean pool. A mean pool is simple, basically a fancy way of saying you just average it out. All the K matrices, you average them up. right? Create one matrix. That's the KMQ matrix, and then use that instead. Okay, so now what you do, you actually averaged out all the keys of an existing model instead of training it from scratch, which earlier people were trying to do. So they said that don't do that. Don't train everything from scratch. Take an MHA model and convert that into an MQA model. By first doing this, so this is step one. So this is step one. By first doing this mean pooling, and then in step two, you then do further pre-training. What is further? Further means you were doing the training of MHA. So this was getting trained, and let's say the idea was to to make it go through K epochs, let's say. So what you do is you stop it, you halt, or you stop the training at K prime epoch, get this thing done, step one done, okay, merge everything K, and therefore you have to merge the V also. If you're merging the K, the representative, you have to merge the master also. So you have to merge the V as well, and then start doing the further, complete the further training till K. So from K prime till K. So this is from K prime to K. Finally finish the training, right? So what we saw was, and this proportion alpha. So alpha would be what? Alpha would be the proportion of let's say, so this is alpha. So this is the proportion. So how much proportion? So 0 would mean that you're not doing any kind of step 0. So 0 means no step 2. So that is 0. Versus when you start doing step 2, you see there's a huge jump in the performance, right? So and then it keeps going on as this is 10%. So this is 10%. This is 0%. So as you do this, you see that you start gaining the stability, the training stability, and the performance also starts increasing, right? So that was not happening before. So this is called uptraining. This process is called uptraining, right? It was termed uptraining. So you got the training in stability, but what's still missing is you still get a decline in the performance quality. Why? Because whatever performance increase that you got over here is relative. You will never get the kind of performance that you were getting in an MHA, right? Because already you have made a big assumption that's quite wrong, that your V's do not differ or do not change, and your K's do not change from one head to the other head. So that's not true, right? Okay, so then we in 2023 EMNLP, Google research came up with this new technique, and they said that okay, we are going to do a little modification to MQA, and they came up with this idea called grouped query attention. So GQA, so what GQA is, so it says that okay, so instead of making that big assumption that there is only one V, like me, I am the influencer and I am only one and my personality doesn't change, let's say that yes, I do change, but not that many number of times as you are changing, as the guy who is getting influenced. So the query gets changed every time for every head, but the value do not get changed every time for every head, right? So there are a lot fewer number of values, as compared to what was going on before. But it is not also taking the other extreme, that there should be only one guy. That's also not happening, right? So you're kind of doing the good of both the worlds, sort of, and you group these queries into one sort of a head. So this is H1, and this is, you can group it in 2, you can group it in 3, you can group it in 4, and so on. So if you are grouping more, which means you are decreasing the yellow values, right? So if you want less values, then you will group more. So this GQA becomes an MQA when you group everything together into one group. So when there is only one group, the GQA collapses into an MQA. Simple. So that was the idea. And what we saw was they did some run it over some NLP tasks, on different data sets, and they, like the CNN, the ArcZip, the PubMed, these were the media these were summarization tasks, and multi-news as well, multi-document summarization task, then WMT, the machine translation task, and trivia QA is question answering task. And then they try to understand the differences that one can see, GQA versus MQA and GQA versus the MHA, right? And what they saw was, on an average, the performance of GQA was actually better than even the MHAs, right? And that inference time also, of course, it cannot be like MQA, because you have drastically reduced everything into just one, but it got really good reduction and comparable reduction as compared to MQA. And it only starts increasing from here onwards, the time, which means the groups. So how many number of groups? So which means if the group size is small, then definitely you will end up getting more number of these yellow guys. This yellow, this will increase, right? So if the group size is small, so or rather if the group numbers are large. So that's the thing. And in terms of performance, you're saying something that if this is the best, so you are nearing that best, very near to the best, but at a lot less time, right, as compared to the best. So that's the thing. So final sort of a key takeaway is, are we all set? So the GQA MQA aim was to reduce the need for storing a large amount of KV cache, right? Because the head and the layers, the heads was increasing the KV cache by a factor of 8. So the idea of GQA and MQA, the real aim was that. And because this happened, therefore this also happened, which is the LLM server can now handle more requests, larger batch sizes, and increased throughput, thereby increased throughput, right? But this is the problem. The problem is, we have not been able to, from a time complexity or a speed point of view, we have not been able to significantly reduce the computational load, because at the end of the day, the dot product and the softmax and then the final, that's going to happen irrespective. That's going to happen exactly like how it was happening in KV caching. So you have not reduced that part. All you have done is that, so you have not reduced anything at a single head level. So whatever was happening at a single head level, you have not touched that. All you did was, okay, since it was multiplying across a lot of heads, let's reduce the number of heads. Simple idea. The idea is extremely simple. Since you are doing the same thing across multiple heads, let's reduce the number of heads. But you did not optimize it any further at the KV caching level. That's not something that you did, right? So therefore the quality at a single head level, the quality still is degraded. It still hasn't changed much, right? So that's the thing. So next class, I'm going to talk about, can we actually do better at the single head KV caching level? Can we actually make that better? And the answer is yes. And surprisingly, the answer is that we can actually get an exact performance, like without any approximation, no approximation involved. Whatever was the model doing, we can do the exact same thing, but with a way reduced time. And we will talk about flash attention, so which is currently going on.